Position is a vector. I need to tell you both how far east I am and how far north I am. Displacement is the difference between positions, so it must also be a vector. If I walk 3 meters in the x direction and 2 meters in the y direction, what is my displacement vector? This is a simple sort of problem. We're just wanting the sum of a 3 meter vector in the x direction and a 2 meter vector in the y direction. And that sum can be written as 3 meters x hat plus 2 meters y hat. Note that we include the units here. Now, if we want to know the velocity vector, that's just this displacement divided by the time. So in this case, it's just that displacement vector over the time interval. So suppose it took 5 seconds to do this. Well, then delta t would be 5 seconds. And the way you do the arithmetic is you simply divide each component by that 5 seconds. Again, note that the components have units. Another application of this is to look at a motion diagram or a strobe diagram. Take, for example, a strobe diagram representing a car moving along a curved road. Let me label these by the times. And by this I mean this is one time interval after the first, another time interval, another time interval. If I want to know the displacement between two time intervals, again, I just draw a vector joining those points. And I can label that as d sub 3, 4, which is the displacement from time 3 to time 4. Well, I can use that to then construct the velocity during that time. And to do that, I just take the components of this vector and divide each of those components by whatever the time interval is between when these snapshots are taken. Okay. And of course, dividing by this scalar, that doesn't change the direction of the velocity vector. So the velocity vector points in the same direction as the displacement. The velocity vector always points along the direction of motion. Okay. Well, we can repeat this argument to calculate an acceleration vector. So if I went and constructed this displacement vector, right? This top one we said is v3, 4 times delta t. And this bottom one is v4, 5 delta t. And I get the velocities by dividing by delta t. Well, I can find the average acceleration during this time interval by subtracting those velocities and divide by delta t. And I can graphically make that difference. So if I use that these velocity vectors are proportional to those displacement vectors, this is just d4, 5 minus d34 over delta t squared. Right. Well, let's copy those vectors and try that. So this top vector is d34. This bottom vector is d45. The difference is the vector I need to add to d34 to get d45. So this vector we just argued was proportional to the average acceleration. And so that means the average acceleration is in fact pointing in this direction. That's somewhat counterintuitive, that the acceleration, so that while the velocity always points along the direction of motion, the acceleration does not. And in fact, the acceleration, if you're moving around a curve, always points to the center of the curve. More precisely, there's always a component of the acceleration that points towards the center. So the acceleration, depending on whether you're speeding up or slowing down, it could point in many different ways, but it's always going to be towards the inside of the curve. We'll talk more about this later in the course.